So the talk is about vBNG data plane in P4-Programmable FPGA-based acceleration card. We will start with the picture that you may have seen before. It's the SIBA experimental, example platform, where there's a list of options of where and how vBNG or BNG can be implemented. There can be obviously external physical BNG. Then there can be vBNG in the compute nodes. That's the focus of this presentation. And then the BNG can also be in the aggregation switches or all OLT boxes. So we decided to do vBNG in the compute nodes. vBNG in compute has the flexibility of software because it's running on the server, so it is basically a software programmable, so that it should be really easy to upgrade with new features, to bug fix it, to customize for particular deployments and use cases. It also should scale well with the number of servers, assuming there's a load balancing, for example, in the aggregation switches. And if you want or need to, it can also be standalone. It doesn't have to be really just part of SIBA. It can be also something else. What we need to get right is the price per gigabit per second, both CAPEX and OPEX, and the performance of CPU-only solution can be a challenge here. So that's why we're working on FPGA accelerated implementation of BNG. Our plan is therefore to use commodity server with FPGA accelerator to run performance optimized vBNG. To implement the data plane in FPGA, we want to use P4, and the CPU then should be used just to run the control plane and the, let's say, exception traffic, control traffic, not the data plane. We're part of the ecosystem here because you need to get many layers of the problem right. So starting from the bottom, our target is Intel PAC N3000 FPGA acceleration board, together obviously with the CPUs. Then Netcope is a provider of the firmware for the FPGA compiled from the P4 specification. Then we're working with Benu Networks and with their vBNG software implementation. And Dell is kind of integrating everything together and obviously providing their servers. Now here's the architecture of the vBNG, and we will focus this presentation on the data path, which is Intel FPGA card. And most traffic is processed on this card without ever reaching the CPU. And only some control traffic, exception traffic, and so on is forwarded to the control plane. It's the green arrow. It's forwarded over DPDK and Stratum, so that we're using standard interfaces here. In this picture, we have the vBNG software running on the same machine, but since we're using standard protocols, it could potentially run also somewhere else. Now, the details of the pipeline. We've started with the P4 code that's on GitHub by DT, and actually, if you look into it, there's a bit more than just vBNG. The code is pretty big. It has around 30 matrix tables, 25 counter arrays, so it does a bit more. Fortunately, most of those, let's say, additional features are hidden in ifdefs. Well, not hidden, but can be turned on and off. So things like in-band network telemetry or SP gateway functionality, which are not typically the major part of BNG, can be switched off pretty easily. Then, of course, it's worth mentioning that the code doesn't cover all the features, especially the ones that are outside of P4 language specification, such as QoS. I know that there's been some traffic management working group with the P4 consortium working on potentially extending the P4 language also with specification of traffic management, such as QoS. Right now, the code sets the QoS just as output metadata without really describing how the QoS exactly behaves. Now, the result that we are looking at right now is the pipeline that has the basic features such as input filtering, BNG, NCAP, DCAP. We use IPOE in this case. There's an ACL table and the forwarding tables with support of MPLS and VLANs. The N3000 platform has 80 gigabits per second throughput, and the pipeline that we compile is by design, designed to run at line rate. So 80 gigabit is the throughput that we should be getting from this platform. What's maybe more important, kind of, is to understand the limitations. Unfortunately, there are limitations, as always there are. So what is limited by what? The FPGA logic, the size of the FPGA, will limit the number of tables you can afford to have there, and also especially ternary table size and key width, because ternary matching is difficult by definition, more difficult than exact or LPM. It has to run in parallel, and so it consumes FPGA logic more than most other things. The on-chip memory in the FPGA will limit your other table sizes, LPM and exact match, and also the size of counter arrays you can afford to have there. And then typically there's some off-chip memory, some DDRs available on most platforms. So those will make your exact tables much bigger, but also define the limits there. The same applies to counters. And also what's worth mentioning is the throughput, because as long as you are in the FPGA, everything is nicely parallel and you don't have to worry much about the throughput. It's just everything is happening in parallel. But with off-chip memory, there is some data width and some frequency. You have to fit in this envelope. So the more off-chip lookups you are making for each packet, the lower throughput in packets per second you get. So this is something that needs to be considered when designing the processing pipeline for BNG and potentially also other applications. Our next steps with this project is to do a lot of progress in Q4. We want to employ large capacity tables to use the onboard DRAMs. The capacity of the DRAMs available should get us to millions or tens of millions of entries. So that way we should be able to support much more subscribers per card. Then there's still some integration work ahead, and it should be easier for any next steps, because we're aiming at open standards for extensibility and flexibility, P4 runtime, DPDK. We want to minimize any proprietary interfaces as much as possible. And also, we're looking at first customer trials in Q4. In the next year, HQoS is a major feature that FPGA also can help with. In our case, since P4 doesn't support traffic management specification, we will basically go the same way as already in the code. So it will be separate FPGA module connected after the P4 pipeline, and it will be controlled by the metadata. So the P4 code will just say this is the queue number that this packet goes to, and the following module will just put the packet into the correct queue. Plus, of course, there will be some API to set parameters of the modules, to set the priorities of each individual queue and the rates of the queues. So yeah, that's it. Thank you.
Anyone has any question?
Oh. Yeah, just a quick question on the traffic management. Is this supporting shaping as well as policing, or just policing? Or?
It's going to be more about policing, I would say. We'll have to, yeah, it's policing, basically.
Question regarding the 80 gigs, is that, does that mean 2 cards? Or?
No, it's 2 interfaces of 40 gig Ethernet.
On 1 card? Okay.
On N3000, on one card, yes.
And can you put more cards into one server?
Yeah, the plan is to put up to 4 cards in a single server.
Okay.
Where do you use DPDK?
Let me check the picture. The DPDK is here to transfer any data plane packet when it needs to go through to the control plane. So the card has XL710, which is standard NIC silicon, which exposes DPDK or Linux NetDev interface. In this case, we assume DPDK.
So DPDK running on Intel card?
Yes.
Okay.
Yes, basically yes.
Can you say that again?
Is DPDK running on Intel card?
It's DPDK interface to the Intel card. Yeah, the DPDK is a software framework running in the user space.
Okay.
Just one last. Does it mean that you're encapsulating the entire control traffic into P4 runtime?
Yes, yes.
Is that a good idea?
Haven't measured it yet. But since it can be done locally, it could help with the throughput of this. If we run into bandwidth limitations there, we'll have to do otherwise. But yeah, sure. Craig will provide better answer. He did this picture anyway. So
sorry, is this working? Not really. Yeah, look, there's pluses and minuses of doing it that way. One of the pluses, of course, is you're abstracting those layers and you're providing a standard interface. So the control planes can use P4 runtime and GNMI as a standard way of interfacing into, FPGAs, multiple different programmable pipelines. In terms of performance, it's on, but it's just not working.
it is.
Maybe
I think it is.
turn around this way and talk louder. In terms of performance, yes, you're running DPDK, and in fact, we're running DPDK, from the XL710 up into Stratum. That integration is kind of hidden from the control plane. You don't see that, right? So, there's a Netcope API here. There's DPDK here. That's abstracted. You don't actually see that from the control plane. And so that's obviously one of the benefits. Plus, it's control plane traffic, so you're not talking about data plane traffic. So performance-wise, it's less. Yeah. And the other thing too to remember is that so we talked about 4 of these cards in one server. You could have a logical BNG that's multiple servers as well. Right? So.
Why did you choose Benu vBNG? Was it something special there?
I would say it's more a political decision.
Oh, okay. Thanks.
I have one question. Maybe I don't understand the vBNG too well. Do you need to support the IGMP stuff on board also?
Which
IGMP?
what stuff?
Multicast? No?
Some requires it, some don't.
Some requires, some don't, right? So on your stuff, you don't have the IGMP support right now at this point?
Right now, there's no support yet.
Okay. Any other
Over there.
This is my exercise.
So is the compiler is it working? Is the compiler the standard P4C compiler, or we need
We're using the front end of the standard compiler, but the back end that generates the firmware is our proprietary, because it uses a lot of hand-coded HDL modules for the FPGA.